More seconds and then we start. I realize again that those things might be material that is pretty much new to you, and you might have difficulties digesting all the new concepts that we actually present in the board. But we need to find an adaptive process so you can learn something and at the same time again do well in the exams. So we'll see how it goes. What time is it? Right, okay. Right, before the break, we're discussing a problem that says that if f equals, and I think gives us the expression 2xy plus z to the cube. I'm referring, I think, to the last problem in the tutorial that's about vector calculus. So if f equals 2xy plus z to the cube, and then I plus x squared j, etc., and then if f and phi, they relate with each other that the f as a vector is basically the nabla or the divergence of phi, then find what phi is. And also we need to prove that the f is a conservative field. Yes? Yes? I need the feedback, guys.
Yes.
Excellent. Right. Who said that? 5 extra points to Ed. Ed, is it you who said it?
Yes.
I give you 5 extra points.
Thank you.
And I'm serious. I need the feedback so you can actually move forward. Right. Okay. Excellent. 5 extra points also to Daniel, who answered yes. Excellent. Thank you. Right. Okay. So do you remember how we proved that F was a conservative field? Or what is the meaning of a conservative field? Does anybody remember? Yes, indeed. Thank you very much. How exactly do you spell your name? How do you spell your name exactly? You don't want to talk. That's perfectly fine. Independent of the path. Mr. Alanesi, how do you spell your first name? How do you pronounce your first name? Sorry. My microphone doesn't work, unfortunately. All right, that's perfectly fine. Yeah, I understand. That's all right. I mean, it's difficult somehow, so it's Fawaz. Is that all right? Fawaz. I hope I say it properly. If not, my apologies. Right, okay, that's fine. Right, so it's independent of the path, right? But again, what is the mathematical way to prove it? Because this might be something you need to do during the exam. And there are a couple of different ways that it can be done. I think in this particular case, what we did is we said, okay, if something is independent of the path, we can apply this expression over here, right? This is again the curl. They call it also the curl of f, which is this. That's the way mathematically express it with a nabla cross f. And we expand that, and if we prove that each one of those components, the I, the j, and the k component, all equal to 0, then the k is equal to 0, and this means independent of the path. Now, part of the reason is that another way to say it is that, let me write it again. So this thing, I put it within parentheses, and then ds, well, ds, sometimes you might see it in books that is written this way as well, where n indicates this n with a hat on top of it, indicates the unit vector which is perpendicular to the surface ds, the infinitesimal surface ds. And ds obviously is again so ds over here is basically a vector, but you can write it this way as well. So this is the magnitude of ds, and then n with hat on it is the unit vector. Now this one, there is a law called the Stokes theorem. The Stokes theorem. And see when I will learn somehow to use this tablet properly. The Stokes theorem says that this again can be written as a line integral. So if either of them, again, if this, the integral itself with the sequel, it means like it's a closed integral. So this means basically if you go from the point that you started and end at the same exact point, and obviously if it is equal to zero, it means that it's independent of the path, right? So either way, you can actually prove that this thing is equal to zero, or this thing is equal to zero, whatever is more convenient. Okay, perfectly fine. Right. Okay? So one thing is to prove that this F field, which is given with an expression, obviously is an artificial one. I don't think you find anything practical that might be expressed with this sort of mathematical formulation, but it's again for people for purposes of training to understand what is a field which is conservative. In other words, it's independent of the path. And again, I almost guarantee that one of the questions will be about conservative fields and to prove that the field is conservative. Right. Maybe again, the procedure we apply over here might be different from the one that you need to apply for the exam, but it's a good thing to have at your disposal various ways and procedures to be able to deal with things. Right. Okay. Then we said, okay, that's perfectly fine. So we went through the process. And someone is diligent enough and scholastic enough might be able somehow indeed to prove that the kernel of the F, in other words, this expression over here, for this particular field, which is expressed this way, is independent of the path. In other words, if we express the kernel and find all the coefficients of the I, J, and K components, they're all equal to zero. We feel comfortable with that. If not, we can always revisit it, and we revisit it, because again, I have to make sure that the people at least who continue coming to those 3-4 weeks, whatever we have, they should get more than 80% in the final grade. If not, it's a failure. Are you with me? For those of you who will come and listen and express an interest to learn, I will be disappointed if you get less than 90. Are you with me?
Yes.
Excellent. That's why I want to hear. Because again, there will not be surprises in the exam. No surprises. Everything is going to be in the exam. There are things that you see something similar during those sessions that we have those 2 days, Tuesdays and Thursdays. Of course, there might be a disconnect with whatever things that you learn in the lectures. I think they'll be complementary, hopefully. And at the end of the day, maybe be some sort of suffering because we need to do a lot of things in a very limited period of time. But that's the nature of the game. Anyhow, now let's come back to the problem. Because in the previous time, I was feeling tired towards the end of the hour, and I think I was making mistakes. Anyhow, so we have F. F is 2xy plus z. Actually, let me actually start also the recording. Sorry.
Recording in progress.
Right, so F equals 2xy plus z to the cube, and then this is the I component plus the j component plus the k component. And then we say that if F is going to be equal to the divergence of phi, and the divergence of phi is given by this expression over here with the partial derivatives of f with respect to x, y, and z, then we have to have the partial of phi with respect to x is equal to f to x, but f to x equals is given. So now we go the other way, so we need to integrate with respect to phi, and we find that phi equals, if you see this expression over here, this term over here, if we integrate, why that's right?
Petros, when you're referring to like which integrals, we can't actually see. I don't know if there's a way you can like indicate on the board which one you're referring to, which integral when you.
I think you're absolutely right. That's what I'm trying to do. I myself trying somehow to figure out how to do those things because I took this tablet about a week ago, and I make some silly mistakes as I use it. But thank you very much for your feedback, and I'll try somehow to take any possible steps to mitigate for those things, right?
Yeah.
Okay, so we have again, I'll try, I don't know how to actually show it without writing something. So you can see the arrow at least, right? So please say yes or I can continue.
Could you repeat that, sorry?
Right, we have here an expression for f. Yeah, that's our field that we need somehow to prove, and assuming that we prove that this is indeed conservative. And now we have another function phi The phi is also a function of x, y, and z, right? You see the phi? It's a function of x, y, and z, but it's a scalar. Now, when we take the number of phi, in other words, the divergence of phi, then this becomes the whole thing a vector. And then we again have to equate whatever is the components for f and the components for the number of phi. And that's what I'm doing. Oops, sorry about that. And that's what I'm doing over here. At the end of the day, we have too many vectors without having any field. Right, so the partial of phi with respect to x equals f of x and equals 2xy plus z cubed. All right so far?
Yeah.
Excellent, thank you. So if we are in this relationship here, we need somehow now, this actually been expressed as d phi. I just take the liberty not to be very diligent with my the partial derivatives and the whole derivatives, but I can write this thing over here as this way. Now this is 2xy. And if I integrate that, right, I'm getting this expression over here. I hope. Yeah, so this is this, and then from here, if I integrate, I'm getting that one. Now, this last term over here is another function that is constant with respect to x, so it's a function only of y and z. Is this understood? Yes or not? Someone say yes. What about the rest of you? So now we have phi equals x squared y plus x z to the power of cube plus another function, call it any way you like, but it's only a function of z and y, meaning that it's a constant with respect to x. Yeah? That's again a very, very typical rule of integration. So the next natural step to do it again, we take now this new expression for phi, and we take its derivative with respect to y. So the first term will give us only x squared, the second term doesn't contain any y, so it's 0. And the third one, we just take again the derivative of the new created function, which is g of y and z with respect to y. Okay, so far? So please say yes or no so I can take a breath. Nobody wants to talk?
Yeah.
Excellent, right, okay. Right, so what do you think should be the next thing here? So I have same thing as before, right? We integrate that. We integrate that with respect to y. So from here, if I integrate with respect to y, it will give me what? X squared times y plus the integral of this with respect to y. Oops. With respect to y. Right, if we do that then, the next thing to do, so we call again this new function maybe. If I take now the derivative of this with respect to z, so the derivative of that with respect to z is going to be equal, this going is 0. So basically, the derivative, whatever is here with respect to z, but obviously this has to be a constant. So this function itself, whatever it is, call it f or whatever you want, it's just simply a constant. And that's pretty much, again, is the end of the whole story, because then all we have to do is, again, we come back over here and then substitute for this function a constant. That's the end of it. Is this clear, or you want someone to give more clarifications? Now, to make you feel good, nothing like this will be in the exam.
Yes.
Right, okay. So let's again talk about some things that might be in the exam. Let's then make more clear. So one thing is that if I have, let's say, if I have a positive charge Q, one question might be how the field lines due to this positive charge will look like. Anybody help me with that? If I have a positive charge, have
The
you
lines would be just going out of it, wouldn't it? Because it'd be going positive, negative, so it'd be going outwards.
right? It will be basically radially emanating outwards, and obviously this is in any direction in space. But again, we have to draw it in a plane, so that's pretty much going to look like, right? If it was negative, it would be towards the charge. Then the next question is what will be maybe potential question. I'm not saying it's going to be in the exam, but it's very potential possible to be in the exam. What will be the magnitude of that force or the intensity of that electric field? How are we going to find it? Have you discussed that in the lecture? Have you basically discussed about Gauss' law that tells us that this thing? In other words, the surface integral of the field intensity is going to be equal to the charge enclosed divided by the permittivity, which is in essence epsilon, is the permittivity of the vacuum times the relative permittivity. Have you discussed those things in the lectures?
Yeah, we did. I think it was just you referring to like what the actual charge was. We'd need to know what that is.
Right, okay. So then again, you feel much more comfortable with those things. Now, if I want somehow to apply this expression over there, I need somehow to choose a surface which is convenient for this law to be applicable. Any suggestions? What type of surface should I look?
Maybe just using a sphere.
Well, yes, we take a sphere. What other is specific about that sphere?
Would the radius not be as far as the lines go?
What about the center of that sphere?
As a point mass, why would you treat it as a point mass?
Right. So again, I cannot hear very well. That's why I might again ask questions.
Oh, I'm saying, did you treat it as a point mass?
Right. We treat it as a point mass. So basically, the center of the sphere will be that charge over there, right? So let's assume again, for the sake of argument, that the sphere looks like that because of symmetry. Most of the problems of electrostatics and magnetostatics, we need somehow to make sure we take into for our advantage the symmetry that the description of the problem presents. So if we take that again, everywhere, because of symmetry, the value of E is constant, so you can take it outside, right? And also, E obviously is a vector, so it has a magnitude and it has also a direction. The direction of E is outward, so it's the same exact thing as the direction of ds, because ds itself, it has again a direction which is the unit vector perpendicular to that surface of the sphere times ds. So this can be written then E ds, and obviously E is constant, so it's dependent, let's say, of S, so it can come outside. And we said that the area of a sphere is what? 2 pi r squared, right? So it's equal to Q over epsilon, so therefore E is going to be equal to Q over 2 pi r squared, somewhere there an epsilon, and also has a direction which is basically along the radial direction. Is that okay?
Yes.
Excellent, thank you. Now, I said that this is more like an educational break. I said that the area of the sphere is 4 pi r squared. Do you buy that? Do you accept that?
Yes.
Why?
Because both pi r squared is the area of a square. Or a triangle? Or of a sphere.
Why we should believe that? Why you should accept that? You should always be skeptical. Always again ask the question why. If the person knows the answer, that's perfectly fine. If doesn't, investigate more. Okay, let's attempt to do something here. So this is spherical coordinates. So things are a little bit more perplexed. If I try somehow to express things here in spherical coordinates, and if I do that, what else can I need to do here? Something like this maybe. Always difficult, it's always a challenge for me at least to draw things properly. Well, what can you do? In spherical coordinates, I think if I remember well, the relation between the Cartesian coordinates and the spherical coordinates, I think they're given this way. No, this is cosine, and then sine. Y equals R cosine theta, and then phi actually. This confuses things. And Z equals R sine theta. In other words, there is a way somehow to correspond always Cartesian coordinates to spherical coordinates. But it's always beneficial to be able somehow to draw those things properly enough. Anyhow, I'll leave it not to confuse you further. But again, if you go through this process and then you take the proper integration, you can actually prove that indeed, in the case of a sphere, the surface of the sphere is not 2 pi r squared, but it is 2 pi r squared or 4 pi r squared. Anybody? 4 pi, yes. That's why again, you should always challenge the person who makes an argument, an assertion that indeed whatever he or she says is correct. But anyhow, enough of that. I need somebody to draw properly things in spherical coordinates and then take the proper integration to indeed prove that this is the case. Otherwise, I think what we need to do is we have to take, let me see if I remember well. So R d theta and then R sine theta d phi, right? Is that correct? And then I think you need to integrate with respect to theta and phi. Anyhow, we'll leave it as it is at this point because again, I probably confuse you rather illuminate. All right, fine. But at least now you know how to calculate E. In other words, the magnitude of the electric field in the case we have 1 point charge. Now, what about if I have 1 point charge over here, call it Q, and here another point charge, we call it 4Q. Can someone suggest how the field lines of this electric field of the combined presence of Q and 4Q should look like?
Are they both positive?
They're both positive, yes.
All right, so they're obviously going to be repelling each other, right? But it'll be like, is it 3/4 of a way along? If that makes sense. For like well, actually, no, it'll be like 4 or 5 minutes.
All right. So you said something. So
yeah, so you'd have like them repelling each other, but it would be, I think, like, is it 4/5 of the length between the two of it?
we will figure it out.
Yeah.
So you're suggesting something like this, right?
Yeah.
Okay. So another possible question is, at which point the combined electric field is actually equal to 0? And that's actually the question you just asked. Is it 1/4, 1/3 of the distance? Let's figure it out. All right, so the electric field due to this charge is going to be equal to what? Q over 4 pi epsilon, right? And let's call this distance x. So this one will be, let's say, L minus x, where L is the total length. So here is 4q, 4 pi epsilon, and then L minus x squared. So some of those constants will cancel. So what is left is 1 over x squared equals 4 over L minus x squared. What's the next step? Take the square, right? So 1 over x equals 2 over L minus x. And let's so L minus x equals 2x. So x equals L over 3, yeah? So the distance x equals L over 3, in other words, 1/3 of the distance between the two charges, the combined electric field will be equal to 0. Do we agree with that? Yes, no, or who cares?
Yeah.
Thank you. What about if I have an equilateral triangle and I have at the corners of this equilateral triangle equal charges? Can anybody suggest a way that the field lines should look like? Actually, before we go there, do you guys discuss about equipotentials?
We did potential in the lecture, electric potential. The equation.
What about equipotentials? In other words, the points that they have the same potential.
Well, I think I'd just be using the potential equation, like V equals equation, then doing exactly the same as what you've done there, right?
For instance, let me again ask more specific questions so you'll be able to answer. Let's move to the next page. If I have here a charge Q that again emanates the field lines radially outwards, equipotential means that the points that they have the same exact potential. In this particular case, it's basically it's a sphere. And usually the equipotential are practically perpendicular to the lines. Like over here, the angle is 90 degrees. That's the meaning of equipotentials. Now, if we go to the previous one, and we want to find here equipotentials, it should probably look something like this. Yeah? And over here should probably look like this. So equipotential lines are always perpendicular to the field lines. Yes?
Yeah.
Excellent. Try to remember that. Now, if we have this sort of expression, we have three point charges at the corners of an equilateral triangle. Can someone suggest how the field line should look like?
It'd be radial on the outsides of the cues until it gets close to each one, and then it would probably like repelling away from the center. So it's like the center, there's no field
So
line.
let me start doing some drawings. And oops.
Oh, that are you saying potential lines or?
No. You're absolutely right. I made a mistake over here.
Yeah.
Erase that.
So like really out. I think radial was probably the wrong word, but basically straight outwards from each one. Besides the center of the triangle and between probably the ones where they
give me a second and I'll try to draw it. All right. So basically here it's the same thing as if nothing was around, which is nothing.
Yeah.
And again, as they go closer and closer, it would be like this, right? Is that what you're suggesting?
Yeah, that's what I'm suggesting. And probably like in the center as well, there'd be nothing there, would there? Because
yes, absolutely right. Okay. So again, keep in mind, this might be in the exam. So again, make sure again you understand it. I don't know how to properly grow it, but and if we want somehow also here to draw the equipotentials, remember the equipotential is always perpendicular to those lines. So just basically do things that are perpendicular to that, right? The moment you have the lines of an electric field, then the equipotentials are always perpendicular to that. Yes?
yeah.
Excellent, right. What else to do? If we have a rectangle, and again I have can someone suggest in the center of this how we're going to be the various fields? And actually, let's make this minus. Let's make this minus. So this is positive. This is positive. And those are minus. Can someone tell me how is going to be the electric field at the center of that rectangle, or actually square? So we have two positive and two negative charges, and we're looking to find what is the intensity of the electric field at the center of this square. Does anybody want to help me? Did I express the question properly enough? Or managed to confuse you?
Are you referring to tutorial 2 now, or are you still referring to the first tutorial, the vector calculus one?
Well, we finished with the vector calculus. I don't think there's anything else there that we need to discuss, unless you want to discuss something. So now we move a little bit more into something that it might show up in the exam, and then we can do the tutorial 2. Because again, we can finish tutorial 2 today and the day after, like on Thursday.
Okay.
Do you have any particular problem in tutorial 2 you want to discuss?
Yeah, but whether we start that now, I don't know, or whether you.
Yeah, we can do it now. Absolutely right. Do you know what the problem is?
Yeah, and the first one,
But do you remember it? Because I don't.
Yeah, I got it up here. Like, yeah. Do you want me to share my screen and just take a screenshot?
Let me make you somehow co-host. What's your name, please?
Ed Robson.
Ed Robson, right? Okay, I'll make you co-host and then. Right. Your co-host now.
Cool.
Share your screen.
Right. Okay. 1
So I
second.
need to stop sharing my screen though, right?
Yeah. Just bear with just 1 second.
Okay, let me do it. Let me stop sharing my screen here. Okay, stop sharing. What did you say here? Got it, yeah.
Actually, Pedro, would it make sense if I just email you it like right now?
No, that's all right. That's all right. Go ahead. Show me what is in your screen. You can share your screen now, right?
I can. Yeah. Can you see that one there?
Oh, it's too small though.
You know. How's this going?
All right. Can you please read it so I can see? So it says 4 charges or 2 charges.
Yeah.
Point charges.
There you go. Can you see that now?
Yeah, point charges Q and minus Q are placed at minus A00 and A00 respectively. Find the electric field at any point in the XY plane. Determine whether there is any point in the plane where the magnitude of the electric field is 0 and so specify the coordinates in terms of A. Determine a mathematical formula as a function of R for the electric field as R goes to infinity. Sketch the electric field lines in the vicinity of the 2 point charges.
Yeah. Have you took a photo of that, or no, I can probably go through it? I'm not too sure.
Right. So you want to do that problem? So we have the solution, right?
I don't have the solution. No, I just if you can go through that, that'd be a real help.
Let me ask you this. So you don't have access to the solutions?
I don't, but I have had IT issues, so perhaps there is online. I'm not sure, but it would be helpful, maybe regardless, to go through it.
My understanding is that again, the solutions is in the same exact place where basically they have tutorial questions.
I've attempted all of them, but I haven't been able to attempt this one. So regardless, it would be handy to go through it. Is that possible?
Okay, let's try to remember it and then I'll try to solve it. All right, so we have point charges Q and minus Q placed at A minus A00 and A00 respectively. Find the electric field lines at any point in the XY plane. Okay, let's do it then. So you start sharing your screen.
Yeah, there you go.
And I will share my screen. And okay, we don't need that anymore. Right, okay. So we do have the minus A, we have charge Q. And a plus A, we have charge. Is that what it is?
Yeah, you got point charges Q and minus 2Q. And I placed the 2 vector coordinates, I can tell you now, which is minus A00 and A00.
Right. So this is minus 2Q.
Yeah, so that one's Q and that's minus 2Q. And they place the 2 vectors. One is minus A00 and the other one is A00.
Right. As far as it concerns the field lines will be something like this, yeah?
Yeah.
So that's not an issue there. And those now the next question is, at a certain point, the electric field should be equal to 0.
It's saying find the electric field at any point in the XY plane.
Right, okay, that's also relatively easy. So basically F1 is going to be Q over 4 pi. If I take any point over here, does it say in the x-axis or any point?
It says at any point.
Okay, so let's take a point here, for instance, point M. Yeah?
Yeah.
So the electric field due to this charge is going to be something like this. And the intensity of this field is going to be equals to Q over pi, 4 pi epsilon, and then this distance, whatever it is, R1 squared. and this is going to be in R1 over R1. Does this make sense?
Yeah.
Right. Now, for that one, it's going to be something like this. Assuming this is positive, the charge we put over there is positive. So it's going to be towards that. So it's going to be F2 equals minus 2Q, again 4 pi epsilon, same thing R2 squared, and then again why it doesn't, okay. So R2 unit vector in this direction, right? And then when you find those two, you need somehow to combine them to find what is, you know how to add vectors. You create a parallelogram, and that's the diagonal of that parallelogram that gives you. Now, of course, we need to have some more information over here to actually calculate what is the exact value for those things. In that respect, we need to know exactly what is, so you can express it here in terms of values, but if you want some specific arithmetic value, we need to specify what is the exact coordinates of the point that we're looking, what is the combined electric field. Does it make sense?
Yeah, that makes sense.
Right. Now, with respect to where is the electric field is equal to 0, as you can see, at any point different from belonging to the x-axis, we always would have a component that is different from 0. So if there is a point, it should be in the x-axis, right? If there is a point that the electric field is equal to 0, it should be in the x-axis. Well, basically, the electric field due to the q and the electric field due to the minus 2q, they will cancel each other. Do we agree or not?
Yeah, I agree.
Right. Okay. So let's assume a point. First of all, is it possible to be between those two charges, or has to be somewhere else? I mean, the point can be between the charges. It can be here. It can be there. What do you think it might be?
I'm not sure.
Question: can it be between the 2 points?
Could you repeat that question? Sorry, Petro.
Right, that's all right. We have Q. I put some point A here and point B. So we're looking for a point between somewhere on the space that the combined electric field is equal to 0.
Okay, so
and we agree, tentatively at least, that it has to be along this axis.
Right.
Right. Now, the next question is, can it be to the right of point B?
No, because wouldn't it be to the left?
Let's make some more thoughts, right? If we assume the point we're trying to find the electric field, we place the unit of positive charge, then due to the charge at Q, that should be a repelling force, and due to the charge at B, in other words, the minus Q, should be an attractive force. And that's part of the reason it cannot be between A and B, because any point between A and B, the electric field is always from A to B. Do we agree with that?
Yeah.
Right. Now, it cannot be to the right of B, because the force due to the minus 2Q should be always bigger. So it will be always larger, because obviously 2Q is greater than 1Q. So the repelling force, because of the charges at B should be always bigger than the force because of the charges at A. Do we agree with that?
Yeah, I agree with that.
Right, excellent. So the only place that this point can be is to the left of A. Yes?
Yes.
So let's choose an arbitrary point, call it C. And let's call this distance from C to A, let's call it X, right?
Okay.
Okay, so what do we have then? We have Q over 4 pi epsilon x squared. And this is in the direction away from Q. This has to be equal to minus 2Q, right? Now we're talking about magnitude over here, so it doesn't matter if it's Q or minus Q. So this force is going to be like this. Yeah?
Yep.
And the force, because the charge the B should be like this. So we want to figure out whether those two forces are the same. So what is the distance from C to B? What is it?
It'll
Yeah?
be x plus what, 2a?
2A squared, right? Yes, it's x plus 2A, but again, we have to put square.
Yeah, because of the times, yeah.
Yeah, the Q also leave, right? So we have, and then if we take the square root, we have
Oh, it's the x.
x plus 2A equals square root of 2x. Yes?
Yes.
And then we have to do again, solve for x. In other words, square root of 2 minus 1 times x equals 2a. So x equals 2a over nothing. Do we agree, disagree, or who cares? Again, the important thing to realize that the only place we can see that the entire, let's say, place can be separated in various sectors. And the only sector that this is possible is to the left of the charge, the positive charge Q, to the left of point A. And then it's up to you how you go to approach it. You call it the distance x, so the other distance x plus 2a, and then solve the equation.
Okay.
Is that okay with everybody? Is that okay with everybody? Actually, I think I have. Do you want to do any other problem from tutorial 2? Let's go and I'll do the following. I think I have the solution. I have access to the solution. So let's check the solution as well, provided I know how to operate that. All right, so stop saying here. Right. Just give me a second, please. Coulomb's law tutorial questions, Coulomb's law tutorial questions, right. All right. Okay. Can you see the screen now? Can you see the screen? Hello?
Yeah.
Right, okay. Well, I'm just wondering whether or not the rest of you have access to the solutions. So I don't have to go and write everything. Okay, so I read it. If you can see the screen, then we can go through it. If it's any problems that we need somehow to address, we can do it. Okay. Right. So point charges Q and minus Q are placed in those positions respectively. Find electric field at any point in the thing, and then it goes through the process. Pretty much the same thing we did it, maybe we slightly using different symbols. Determine whether any points on the plane where the magnitude of the electric field is zero and so. Right. Is this clear?
Yeah.
Right. Or you want to go step by step with just to give more emphasis details? This is your time. You can do whatever you want me to do. I can do whatever you guys tell me to do. So in the first thing, he finds, let's say, the electric field, I guess, density due to the Q, and he finds electric field density due to the minus 2Q, and then combines the two. But again, he does it by also taking into account that those are basically it takes into account the specific locations of those charges. So the one charge is at the x minus a, y, z, etc., etc.
How come the answers that you provided are completely different to the ones on the solutions? Just obviously you solve for x, whereas that's given a general equation for the total field.
That's because again he's using the x he's using is different from the x I'm using. For him, the x is he takes into account that the x I used was the distance from the Q, while the x he's using is basically the distance from the center of the coordinates. And that maybe it's what the difference in the solution is.
So which one's the correct answer?
Both of them are correct. As far as they're consistent, both are correct. But let's go again through the solution he gives. Because again, you can have both of them. As far as you're consistent, and as far as you clarify what is the meaning of x, because I was taking x as the distance to the left of the point charge Q. He's taking x as being the distance from the center of the coordinates. Is this clear? Okay, let's go step by step. So obviously, again, it's a superposition problem. The first equation, is it clear? So E of Q equals Q over 4 pi epsilon R Q square R Q with the indicator that this is a vector. Is that understood? Can you see my arrow? Oh, you must see, right? Can you see the arrow, right?
Yeah.
Right, okay. So we understand this expression, yeah? And it tells you here that the RQ with the R on top of it is basically that. Please let me know if there's anything here that is not clear. Do you want to do it in a whiteboard based on his way of defining what is X is?
Yes.
Okay, let's do that then. I'll just stop that. Stop the screen. No. Right. Okay, so we have the Q here, we have the minus 2Q there. This distance is minus A, and this is A. So if I take any point here, right, in the space, this one basically and this is the center of the coordinates. Basically, the X is X plus A, Y, Z, and this is X plus A, Y, A. So if we want somehow to figure out what is the, because of this to here, right, the electric field intensity is this one, 4 pi epsilon, and then R Q square and RQ unit vector, where RQ so the RQ basically we need to express it in terms of its coordinates, which basically I think X so basically you take those things and you square them. Yeah, and then also you have the unit vector. I think that's the only difference, but this puts in a complexity which is not necessary. Because all you can say is again, how do you express it more clearly? Do you understand what I'm talking about, or I'm confusing you? If we assume we have what we have here, the X distance is this distance, right?
Yeah.
But this one is again, this by coincidence now, 2Q, let's assume here. This one is basically, if I want to find that thing, I have to add to x this distance, which is a. Yeah, so we have x plus a square plus y square plus z square. That's what RQ square is. Does this make sense?
Yep.
Likewise, for that one, the x is in essence, if the minus u, let's say, was here, right? This point over here. So the x is this distance over there, which is basically, actually, the x is this distance, which is basically I need to subtract from x a. Does this make sense?
Why?
Because again, if minus 2q is here and the point of interest is there, the x coordinate of the point is this distance here. The distance though from the point of interest to the charge is only this small distance. And this small distance is basically x minus a, yeah?
Yeah.
This is the distance of interest. That's why it goes actually in the denominator as r squared. But this small distance over here is this distance, which is x minus a, which is the distance of the point of interest minus q from the center of the coordinates.
Yeah.
Everybody happy with that?
Yeah.
I can't remember what exactly it says then with respect to how to define. Again, we all agree that then the point of the potential point that the electric field from the superposition of the two electric fields, it has to be to the left of point A. Because the electric field due to that is stronger from the electric field due to that, so it has to be somewhere to the left of point A.
Mm.
And then it's up to you how you define the distances for the various parameters. So let's make it more clear possibly. So this is the center of coordinates. This minus 2q. This is q. And that's the point of interest. It depends how do you, if you call this x, then this distance here is what? What is this distance? From this point to that point is x minus a, right?
Yeah.
And what is this distance from here to there? Is x plus a.
Mm.
So as far as you are good in keeping, let's say, things into order, it will not be a problem.
Mm.
But for maybe someone decides and says, okay, I want to call not this x, but I want to call this x, or whatever you want to do. It's up to you. As far as you're consistent and you don't make arbitrary assumptions that you're not following, every solution is perfectly fine. So let's assume again we do that, and let's see what's going to be the final equation that you need, because you need eventually to find the same exact solution in here in the, all right, so let's assume x is this one, so this distance is x minus a, right? We agree with that?
Yeah.
So E1 is going to be q over 4 pi epsilon, and then that one, right? And this has to be equal to this expression 4 pi epsilon and then x plus a squared. Yes?
Yeah.
So if we solve that, are we going to find the same solution? Let's see. So 1 over x minus a is square root of 2 x plus a, yeah?
Yeah.
Right, so x plus a equals x minus a. Square root of 2. Is that minus or plus? That's one thing. I don't think it matters because again we take the right. So the square root of 2, square root of 2 minus 1 times x equals a 1 plus square root of 2. So x equals square root of 2 plus 1 over square root of 2 minus 1. That's not the solution he found, right?
Okay.
It's a different solution, isn't it?
Mm.
Right. Okay, let's do the following. Let's go back to the solution that he provided to check to see if they're correct. Just give me a second, so I will. Let's stop saying that. Right. So determine whether at any point in the past where the magnitude of the electric field is 0 and so specify the coordinates in terms of A. Right. Well, it's slightly different approach, so we need somehow to pay more attention then. Let's go here step by step and see what he does. The first one is pretty straightforward, Q over 4 pi epsilon RQ square, right?
Yeah.
And then RQ is basically x plus a, y, z. I think we did something similar.
Mm.
Right. It's a vector from the point charge to the point x, y, z, etc. Similarly, the charge gives rise to the field. So this was for the first part of the problem, so it's very generic, it doesn't find any solutions. Right, okay. The difference is when he puts them into a final expression. Now, the 3 over 2 here, do we understand where it comes from?
Two.
The 3, can you see the 3 over 2?
Yeah.
It's because, again, it takes the unit vector and he expresses it in terms of x plus a, I plus y, j. So assume there is no k component, and then again, he takes the magnitude of that, and the magnitude of that, that's why you have the square plus the square root, so it eventually gives again 3/2. Is that understood by everybody? Yes, no?
Yeah.
So this RQ over here, it's a vector, but we can express it as it's a unit vector, and a unit vector is basically a vector itself divided by the magnitude. And the magnitude is just simply RQ, right? And so RQ is, and there is another Q also square, so RQ and RQ squared is basically RQ to the third power. Yeah?
Yeah.
I'm trying to explain where this 3/2 comes from. Of course, 2, because again, when you take the magnitude of something, you have to take the square root of that.
Yeah.
So this makes sense, isn't it? Is
Yeah.
anybody who still has difficulty understanding it?
Yeah.
Yes means there is difficulty, so it's clear.
It's a little bit clear.
It's clear. All right. Okay. Now let's go to the next question then. So determine whether there is any